This is joint work with Suresh, who's right there, who I will have answer all of the hard questions. And his undergrad students, Danny and Scott, and a colleague of ours at the University of Arizona, Carlos. So this is about predictive policing. So very basically, the first question we should ask is, what is predictive policing? And this can actually focus on a number of different things. It can mean a number of different things. It could mean that you're trying to predict where to send police on any given day based on some sort of historical crime data. It might mean that you're trying to predict who to target for surveillance, or even who you think is most likely to be a victim of a crime in the future. In this case, we're going to look at the version that is most commonly deployed, which is trying to figure out where to send police on any given day based on historical crime data. And there's an assumption here. This particular assumption, I think, is fairly realistic, which is that you've divided the city into some non-overlapping districts. So essentially, you're saying, I want police to go patrol this neighborhood. There's also a larger caveat, which is that for the rest of this talk, I'm going to talk about this crime data as if it is just arrest data. And in fact, crime data is more complex than that and includes things like reports of crime and so on. And I'm going to come back to whether or not this is really a caveat to this work sort of at the end. So, for now, just assume that this is all fine, and then we'll sort of make it a little bit more complicated right at the end. So the concern that we're looking at is, suppose that you have some deployed batch machine learning process, right? So you have some set of training data and you train it, and then you go out into the real world and you collect new data based on that training data, and then you come back and you add it to the algorithm. In the case of predictive policing, this is police go to a neighborhood, they observe and record crime. Those crime observations are added back into the training data, the model is retrained, and then police go back to the same neighborhood. Right? And we've actually already heard a few people sort of talk about this idea and this concern. I think Meg mentioned it in her talk about this idea that, you're sort of teaching the model that this is the high crime neighborhood by repeatedly sending police there to gather more data that reinforces that notion. And that's a concern that's not just specific to predictive policing. Right? In fact, we can see these same sorts of effects in hiring and in recidivism prediction, where you can imagine that there's some company that has historically hired a lot of white men and, trains some algorithm that says to hire more white men, and so it does, and so says, great, we should hire more white men, right? And this sort of keeps happening. I'm going to talk about it here in the context of predictive policing, though. And so just to give you an idea of this, and this is also an algorithm that we'll be using throughout the rest of this paper. One predictive policing algorithm is Predictive. This is used in LA and some other large cities in the US. And they describe it as an earthquake aftershock model. So the idea is that you're trying to predict, so lambda R of t is the sort of underlying true crime rate for some region at some time, right? So you're trying to predict, is there crime in some neighborhood tomorrow? And the model that they use for this essentially says, okay, was there crime there recently? We can think of this as sort of the earthquake that was the crime. And the idea is that if there was crime there recently, then there's going to be sort of these aftershocks, right, sort of close in time to that big event, and then the likelihood of those will sort of trickle off over time. They also have a version of this that takes location into account, right? So we're looking at the version where we're just looking at a specific neighborhood over time. They also have a version that sort of assumes that those aftershocks could happen in neighboring regions, and we're not actually going to look at that here. Christian Lohm and William Isaac, Christian is right here, did some nice research last year to demonstrate this issue in practice, right? So until this paper, people had sort of been saying, oh, predictive policing, this seems worrying, but we hadn't actually seen empirical evidence that it was worrying. And their paper last October was able to show that, in fact, this effect does happen. And more specifically, they were looking at historical drug arrest data and comparing that to predicted drug usage as sort of an underlying true crime rate for drug use. Using the Predictive algorithm, they were able to show that some neighborhoods were repeatedly targeted for policing if you sort of took this historical arrest data and used the predpol algorithm to determine where to send police next, right? You kept going back to these same neighborhoods. Those are the sort of bright red neighborhoods there. They're bright red because their police are being sent there more than 300 days in a year, right? So they're really being heavily policed. And I guess I don't have the map up here, but the actual drug usage, as you might expect, was much more evenly distributed, right? People use drugs everywhere. So this did not match those underlying crime rates, right? And what's more, it was differential based on race, right? So these neighborhoods that are being targeted are the minority neighborhoods in Oakland. So this seems bad. It seems to demonstrate the effect that we've been worrying about. And our question was, well, why, right? What is the mechanism that is causing this? I mean, we know sort of in a more complex way what the algorithm is that's being used, but can we try to simplify this down to an understandable theoretical model of what's going on that's understandable enough so that we can start to make some interventions to try to correct some of this? So that was our goal sort of going into this, was to say, okay, can we come up with a theoretical model that shows these problems, right, that demonstrates that these problems happen on our toy model, and then can we develop a theoretical solution within that? And then can we also actually apply that theoretical solution back to predpol, right, which is no longer this sort of simplified model, but the real thing, and show that it works in practice there. So a few more goals and assumption caveats first. So our goal here is effective policing. And the idea here is that we want the percent of police we send. In this case, I'm going to imagine that we just have two neighborhoods to keep things simple, right? We're trying to divide some police force between these two neighborhoods. The idea here is that if 60% of the crime is in one of the neighborhood and 40% is in the other, then the neighborhood with 60% of the crime should get 60% of the police. The neighborhood with 40% of the crime should get 40% of the police, right? And the sort of rationale behind that is that if you imagine that you actually had enough police to somehow police all of the crime, right, then this would be sort of the perfect division of labor. So we're calling that effective policing. And then we're actually going to use essentially a very simple model that says, okay, we're going to try and keep track of the relative crime rates in these two neighborhoods. We're going to flip a coin based on what we think the crime rates are, right? Maybe it's that 60-40 split. We're going to flip a coin and we're going to decide based on that where to send the police. Okay. We're also going to assume that the only information that we're maintaining about the crime is the count, right? The existence of the crime at a certain time in a certain region. In other words, we're not going to keep track of any information about the suspects or their demographic information or whether the crime was a felony or a misdemeanor or any of these other added pieces of information. We're going for sort of the simplest model here. We know, there was 1 unit of crime in this neighborhood at this time. And then this last one is the sort of large assumption. The large assumption here is that we're going to assume that if an officer goes to some neighborhood and that underlying ground truth crime rate, right, the rate at which people are actually using drugs in their houses is lambda, then we're actually going to observe crime at a rate of lambda, right? We suspect that this is not true, right? What we are trying to do here is really, this is sort of giving the predictive policing algorithm the benefit of the doubt. This is saying, like, if we put this algorithm in the most ideal circumstances, where every time they sent police to this neighborhood, they saw actually a true amount of crime and were able to correctly record it, would this work, right? So that's why that's such a strong assumption. Okay, so we're gonna build for our sort of toy theoretical model of how predictive policing might work. We're going to build off of generalized polya-urns. And the idea behind urns is that you have some urn and it has red and black balls. And we're going to pick a ball from the urn. And then we put the ball back. And then we're going to add more balls to the urn based on this matrix. Right? And the standard polya-urn would say, okay, you pick a red ball, you put that ball back, and you add one more red ball. Right? So it would have ones along the diagonal and zeros along the cross diagonal. And what this is essentially doing is it's sort of reinforcing the effect, right? it's sort of saying, so we're imagining here that now these different color balls are going to become different neighborhoods, right? So it's a way of sort of saying, okay, I went to this neighborhood, I saw some crime, I want to reinforce the fact that that neighborhood has crime, so I'll add another ball back in. And that brings us to how we're going to use these polyurns as our model, right? So the polyurns are going to be maintaining our understanding of what the underlying relative crime rate is between these two neighborhoods. Right, so if the underlying true crime rate between the two neighborhoods is 60-40, then our goal is to have 60% red balls and 40% black balls in our urn. So each color is a neighborhood, and then drawing a color represents sending the police to that neighborhood. Right, so we're going to draw a color, we're going to send the police to that neighborhood, and then we're going to give some feedback to that urn based on what was seen in that neighborhood. And our goal is going to be to have this long-term proportion of the urn represent the actual crime rates. And again, note that assumption, right? We're assuming here that we're observing crime at the true underlying rate, right? And that rate exactly is the urn replacement rate. So that matrix before, so lambda A is the true crime rate for neighborhood A, lambda B is the true crime rate for neighborhood B, and that's the number of balls that we are going to put back in, right? And in fact, what's going on there is that when we observe a crime, we're going to put that crime back in, right? When we haven't observed a crime, we can actually think about that in sort of a traditional polyurn style as those crimes are spaced out appropriately so that it's the equivalent of putting back in this fractional lambda A number of balls each time. Okay, so now that we have these replacement rates, we can fall back on some of the polyurn machinery. And it turns out that if we have a matrix that looks like this, then as we keep sampling, right, what we care about with these urns is, okay, as I keep sampling and I keep replacing and I keep sampling and I keep replacing, what do the sort of relative crime rates converge to? And if the crime rate in neighborhood A is greater than the crime rate in neighborhood B, then we will end up having only neighborhood A balls. Okay, so what does that mean, right, practically? It means that if the crime rate in the two neighborhoods are at all different, right? Maybe it's 51% of the crime is in one neighborhood, 49% of the crime is in the other neighborhood, right? Our urn will converge to having only crime from the one neighborhood that's slightly more. It will converge to sending all of the police to that one neighborhood that has 51% of the crime, which we had stated up front was not our goal, right? Our goal was to distribute the police according to the relative amount of crime. Okay, so we've now reached a stage where we have a model and we have a theoretical problem with the model, right, based on what we said we wanted to do. So we also wanted to run this experimentally, right? We have a little toy model, we think it has a problem. Does it actually demonstrate this problem if we run with data? So using the data from the Lum and Isaac paper, this historical arrest data from Oakland, we looked at the districts that had the top 1 and top 2 number of arrests. And we also looked at the district that had the top number of arrests compared to some random district. And then we looked at this estimated true underlying drug use rate. And we compared what happened if you tried to divide police between these pairs of neighborhoods. And so what's going on in these charts is that the black cloud, which is over multiple trials because of the randomness, the black cloud is the distribution of how we're sending police, right? So when it's up at that top line, that means that we're sending all of the police to that neighborhood that had the most historical arrests, right? And if it was down at the bottom, that would mean we would be sending all of the police to one of the neighborhoods that didn't have the most number of historical arrests, but it's not. And you might not even be able to see it on the chart on the right, because it's just sort of a black line right at the very top. But in fact, both of these converge to sending all of the police to that one neighborhood that had more historical arrests. And note that also this is not actually the true crime rate in that neighborhood, right? The other neighborhood does have crime, okay? Okay, so what can we do about this? So what we're doing about this relies on this observation that, in fact, if you send police somewhere that you think has a lot of crime, you shouldn't actually be surprised to find crime, right? Or really, there's only a certain number of times that you do that it would be reasonable to be surprised, right? So if you think that some neighborhood has 60% of the crime, and you find 90% of the crime that you found in that neighborhood, then that should be a surprise, right? That doesn't match with what your current statistics tell you should be seeing. And so in that case, you should do something to correct your model. If, on the other hand, you think that the neighborhood has 60% of the crime and you find 60% of the crime in that neighborhood, you shouldn't then say, oh, I should update my model. That neighborhood has a lot of crime. So this leads to a slight modification of our urn, right? So now, as before, we're going to have our urn with our red and black balls. We're going to pick a ball from the urn. We put the ball back. And now we're going to sample another ball from the urn, okay? If that new ball color matches the old one, right, then that's not a surprise. But if it doesn't match the old one, then we put the new ball back in. Right? So we only put a ball back in if the colors were different. And this is similar to importance sampling. Right? Essentially what we're trying to say is, how important was that crime that we observed in terms of correcting for the model? Okay, so we run the same experiments, right? We again run this through our urn. And now this red line in the two experiments on the right is actually the percentage of police that we're shooting for sending to neighborhood A, right, where the rest are sent to neighborhood B. So in fact, the sort of relative crime rates between both of these pairs of neighborhoods was fairly close to even, right? One of them actually did have a little bit more crime, but it wasn't actually substantial. And you'll see now that in both of these cases, we do actually converge to correctly estimating this underlying crime rate. Okay, so that was all well and good in our pretty urn model, right? Does this actually help us with predpol, which was the original question? And it turns out that it does, though you'll note that it is much more noisy, right? So on the left is what happens with predpol over, again, multiple trials between these two neighborhoods. And you'll note that it mostly converges towards sending more police to the neighborhood with more historical arrests, but it's also actually just very noisy, right? On the right is the version where we applied this improvement policy, right? Where essentially we didn't include back some of these arrests to give predpol more information. We used predpol as sort of a black box model, and we either fed it the data or didn't based on whether we thought it was actually a surprise for predpol. And that actually converges, still, again, it's not a tight convergence, but I think it's clearly better, right? It's more closely aligned to that underlying true crime rate. Okay, so, yeah?
Just understanding why the qualitative when you have top versus random, actually the predpol seems to be spreading more versus top 1 versus top 2, which should be more similar, right? Like so in some sense the behavior on the left-hand side is reversed when you do predpol versus your earnpol. At least like just eyeballing it, it's tough to say. Right, like, so remember,
Yeah, I see what you're saying. You're saying it seems like it actually converges faster when there is less disparity between the historical crime rates in the neighborhood. I agree with that observation. I don't have any idea why. Do you have any idea why, Sorelle?
I'm not sure I'm reading the same thing from the
Okay. Well, so maybe there's some argument in the noise.
Yeah. We can talk about that.
Yeah. Okay, so some I'm told quick discussion. So this crime reports versus arrest data, right? Does this mean that this whole sort of observed issue is just not an issue at all? I would argue that it's still an issue, right? And here's why. So crime reports or crime data broadly usually includes arrest reports, right? So this sort of subset of the data on which we see this effect is generally included in the broader training data. Also, we suspect that you're going to see this effect as long as the crime data used is somehow influenced by the police deployment. If the crime data is not influenced by the police deployment, that seems maybe worrying for other reasons, right? So if your crime data is influenced by the police deployment, right, then we would expect to see some sort of feedback loop that you would need to correct for. I also wanted to note that we can actually use this in a sort of a black box way, right, which can be useful, right, because then it allows people not to have to entirely re-engineer their system. If, on the other hand, you wanted to sort of design a system worrying about the feedback issue from the beginning, we would recommend the reinforcement learning take that's on our poster over there, which maybe we'll see later. So that's it. Thank you.